some WHSH here, those things go away. So the numerator just becomes some WHSH quantity squared. And then the denominator. Okay, other questions?
You could just put a 1 as a placeholder and just run it the same way, right?
Sure, that's fine.
For when you're looking in the third question, when you're looking at finding out which estimator, the regression estimator or the ratio of means estimator is more appropriate, what you want to look at is the standard deviation. Not the standard deviation, but the standard error.
Not for more appropriate. The first thing that you would want to look at for more appropriate is which assumptions are satisfied or not satisfied. The two estimators have different assumptions behind them, which we talked about and illustrated with those graphs.
Oh, you mean like there's a linear relationship
Yeah.
and there's the same variability and like the
Or
y-intercept?
not, or y-intercept and so
Okay.
forth. If they're both appropriate, not saying they are. If they're both appropriate, then you'd want the one with the smaller standard error.
So on Wednesday, you were explaining equation 12.2 and explain the different variables. And for SSX, I wrote down that you said that was a numerator of the variance of x.
Yep.
But then if you look at equation 1.1, it has that same designator, but it's also divided by n.
No. Okay, so let's
I'm
make sure.
just wondering if I misheard you. I'm like 80%.
No, everything you said is right except the last thing.
All right.
So we're talking about this thing right here, right? Yeah. So that is the numerator. Its name is the corrected sum of squares. Which means it's also the numerator of the variance formula. Okay, so that's correct. That's what you said. That's what I said. Now let's go back to 1.1. Yeah. That's how you compute SSX. 1.1 tells you how to compute SSX.
Okay.
Yeah. So all that's in that first equation we looked at is SSX. Equation 1.1 tells you how to compute SSX. So that's just the formula for it. But the easier way to get it is what I mentioned last time. Calculate the variance and then multiply it times degrees of freedom.
Okay.
But that'll give you the same thing as that formula. They're the same. That's what we called back in old man's days, me being the old man, the machine formula, or corrected sum of squares. Other questions? Yep.
Just to clarify, you said the easier way to do that is just calculate the variance times the degrees of freedom?
Yeah. Calculate the variance and then multiply times degrees of freedom. It's the same answer.
For the third problem, we don't have a big N, as far as I can tell. We don't have a full population, so we're to assume that that's an infinite
Right,
population.
so the answer to that was hidden in a response to somebody's question, actually, on Moodle, but that's fine. So what I said was what we're dealing with here that are sample units that are essentially points. And how many points can you fit in any area? An infinite number of points. So cap n is infinity. So you can use the finite population correction, but it'll be 1. Yep. Oh, good. Glad you raised that again. Because I didn't create another item. I just included that in response to another question. Other questions? Okay, so it sounds like people are pretty well along with the homework. That's good. So the two slides I didn't get to last time are a continuation of what we looked at before, right? We introduced simple random sampling first, and then applied it to our disc, population of discs, 54 discs, and looked at the sampling distribution of the estimator. That would have been Y bar in that case. Then we went to PPS sampling. Well, actually, it wasn't Y bar, it would be Y hat. The sampling distribution is for the total, not for the mean. And we went to Y hat, we went to unequal probability sampling. The estimator is Y hat PPS for total. And we looked at the sampling distribution for that estimator for our population of 54 discs. And we saw it was much narrower. Did the same thing for stratification. And again, the sampling distribution of the estimator under stratified random sampling was narrower. They were all centered on the true value. They all give us unbiased estimates. They differ in terms of precision. So the stratified was narrower than the simple random, but it was wider than the PPS, the unequal probability sampling. We explained why that's the case. So I continue along that line and provide you the sampling distributions of our estimate of total using regression estimation for the stem discs again. Sample size of 6, sample size of 12. There's what they all look like. Simple random sampling. These are all for a sample size of 6 discs. Simple random sampling, centered on the truth, skewed distribution, and pretty widespread. PPS sampling, centered on the truth, a much narrower distribution, and more symmetric looking maybe. Stratification, which is 2 strata, big and little, that's it. Narrower, scales exactly the same on all these graphs. Narrower than simple random sampling, but wider than PPS sampling, because we're using more information. And then finally, the linear regression estimate, pretty similar really to PPS sampling, and certainly better than simple random sampling, and in our case of very simple stratification, better than stratified sampling. And I say here linear regression with d squared. Everybody remember why I use d squared as the auxiliary variable?
To create a relationship.
So it's the linear relationship. Okay? You have a question, John?
Well, I was going to say, you said that PPS we got more narrow than your strata, but your strata seems to have a more pleasing distribution, to me anyway.
Well, yeah, I see what you're saying, okay? But that's the case because I forced it to have the same scale here. If I would have used a scale that gave us greater detail, that wouldn't be the case. But I wanted them to all be comparable, right? So I scrunched things together.
Okay.
So it's not as visually appealing.
So just to clarify on this, so these are all showing our standard errors. And so they all are unbiased, but the ones with narrower distribution or a smaller standard error are going to be more precise.
These are not showing standard errors. These are the sampling distribution of these estimators.
But the range.
The standard error estimates the spread of these distributions.
Yeah, so this will tell you the standard error.
Well,
The bigger the spread, the bigger the standard error.
yeah, that's true. That's true.
And so you could say that these are unbiased, but the ones with a narrow distribution or a smaller standard error will be more precise.
That's correct. Yep. Other questions? Comments? I looked at myself in the screen. Okay? Anything else?
the material on the exam next week, is it gonna go all the way up till Wednesday, the last lecture, or
No, if you look at the,
syllabus?
my clever presentation in the syllabus, you'll see that the exam is scheduled before what we actually cover on Wednesday. The dates are correct, but it's listed before, so it'll only cover through Monday. The exam on Friday will cover material through Monday. Okay, so another sampling technique, sort of. Actually, today and Monday, we're going to be introducing, quote, new sampling techniques, but they're just extensions of what we've already talked about, where we're attempting to overcome a requirement of a sampling technique that we've already talked about. Make it more practically applicable. So today it is regression ratio estimation, we talked about on Monday and Wednesday, but with double or two-phase sampling. Remember what we assumed with regression ratio estimation, pure up straight regression ratio estimation, was we just did simple random sampling. We didn't change the plan. Here we're going to change the plan and use the ratio regression estimators. So why? Well, what if we have a sampling situation where we would really like to use a regression or a ratio estimator because it's clear that we have a really outstanding auxiliary variable that's going to make whatever sampling we do more efficient if we make use of that auxiliary variable. But we don't know, or it's unknowable, or obtaining full knowledge is cost prohibitive for the mean of x, or equivalently the total of x. Just not possible to get mu of x with any reasonable amount of resource. But we really want to use that estimator because we can save all sorts of time. We got the auxiliary variable. It's cheap, maybe it's free. But we can't know it on all units without spending way more money than we're interested in spending. Because remember, are we interested necessarily in this auxiliary variable in and of itself? No. We just want to make use of it. What we're interested in is the y variable. That's the variable that's of interest to us. Solution, instead of taking one sample, we'll take two samples, sort of. And so it's called, we changed the sampling plan. We're going to use the same estimators, either a regression or a ratio estimator, but we'll change our plan. We'll take two samples, sort of, and hence it's called double or two-phase sampling. We'll take a large sample, and on that large sample we'll observe only the auxiliary variable. We'll also take a small sample. And on that small sample, we'll have data on both the auxiliary variable and the variable of interest, x and y.